This lecture is going to be all about gas in Ethereum. I'm going to explain what gas is, I'm going to explain why it's a necessary evil for the system, and I'm going to explain what it means for you as a programmer if you're developing smart contracts for Ethereum. So at a high level, gas is just how you pay for the computation that your contracts are doing. So anytime your contract is running, when a transaction is submitted to the network that causes your contract to wake up and have to run some code, you're paying gas for every step that the Ethereum virtual machine takes. And each step is really an opcode, which is an atomic step that the virtual machine takes when it's executing on behalf of your code. So when you create a transaction, you first specify the amount of gas, the maximum amount of gas that you're willing to pay. And that is stored in this gas remaining counter, which you can think of as sort of like the gas gauge for your car, telling you, how much gas you have left to drive around. Now, while your code is executing, every step that the Ethereum virtual machine takes, every opcode that's executed, the amount of gas remaining is going to decrease a little bit. And the amount it decreases is going to depend on which opcode you execute. Some are more expensive than others. So, for example, basic instructions like pushing a data item onto the stack, adding, subtracting, those are all pretty cheap. But there are some expensive operations like writing a word to storage, and you'll notice that the amount of gas remaining goes down quite quickly. And then eventually your code will finish. You might have some gas left over that you didn't burn up, and anything that you have left is going to be refunded to whoever created the transaction. So I mentioned that gas in Ethereum is a necessary evil. It would be great if there was no price, if computation were free and you could run as much as you wanted, but it's a necessary part of the system for a couple reasons. One, gas is used as an incentive to miners to actually include transactions and to find blocks. So if there was no gas, if miners had no way to profit off of including transactions in their blocks, the simplest thing for them to do would be to never include any transactions that required actually verifying complicated smart contract code. They would just mine empty blocks, or maybe blocks with simple account-to-account payments. Okay, so we'd like a way to incentivize miners. Ethereum also pays miners using inflation, but gas is also an important mechanism. Second of all, we want to limit the resource consumption of all the users of the network. If computation were free, and if creating contracts and writing things to storage were free, then you might expect the network could get bogged down with spam transactions and spam contracts. People might just create contracts ad nauseum, and of course every miner would have to store and remember those and execute all of those transactions. So by making everything in Ethereum have a cost, it's a way to limit unnecessary use, spam transactions, spam contracts, and hopefully make sure that if people are executing code, they have at least some good reason to do so. And finally, having gas is a way around the halting problem. So this is a famous result from Alan Turing shown there, that it's not possible to look at a computer program and determine whether or not it's ever going to halt, right, or terminate execution. So if we didn't have gas, we would run the risk of miners trying to verify a transaction and it running forever, but them not knowing whether they should stop, if it would ever finish or not, if they kept trying to verify it. But with gas, that isn't a problem. Since you can't have infinite gas, every program in Ethereum will halt eventually because it will run out of gas. So like I said, every opcode in Ethereum has a fixed gas cost associated with it. You can look these up in a couple different places. The Ethereum Yellow Paper is the authoritative reference. You can also look at code for various Ethereum clients. But you'll get basically a big table for all of the different opcodes that are part of the Ethereum virtual machine, and you can see how much they all cost in gas. And like I mentioned earlier, the costs vary quite a bit. So the basic operations, adding two numbers together, jumping, executing a branch, pushing a data item onto the stack, usually cost a few gas, less than 10. The more interesting parts, the expensive operations, tend to be reading and writing from storage, calling other contracts, and creating other contracts. So in particular, writing to storage is expensive because that's something that miners will have to keep around forever if you don't delete it. And similarly, creating a new contract adds new global state to the system that all of the miners have to keep around. That's why those cost a lot of gas, to try to discourage the amount that people do that. Now, you'll notice something kind of funny here. There's actually some negative numbers. So some operations, in particular, zeroing a word in storage or destroying a contract, those actually have a negative gas cost. And the first thing to say is that there's no free lunch. So notice that destroying a contract, it's less of a negative. The magnitude of it is less than the amount it costs to create a contract. So if you create a contract and then destroy it, you're still in the hole by 14,000 gas. And similarly, if you write a new word to storage and then delete it, you're 10,000 in the hole, even though you are getting 10,000 back when you zeroize the memory. So the way gas is implemented, it all has to be paid up front by whoever creates a transaction. So it's like going to a gas station where you have to pay before you start pumping gas, and you can specify the maximum amount that you're willing to pump. In particular, if you create an Ethereum transaction, you specify two things. You specify what's called start gas, which is the maximum amount of gas that the transaction is allowed to consume. And you also specify what price you're willing to pay for that gas. And that price is denominated in Wei, the smallest unit in the system. So let's go through a full example of how gas metering works in Ethereum from beginning to end for one transaction. So let's say some user Alice submits a transaction to the network to call contract C's function foo, and she says that she wants to start with 100,000 gas, and she's willing to pay 2 Wei per unit of gas. So to verify this transaction, the gas remaining counter will start at 100,000. And notice that Alice's balance has actually gone down by 200,000 because it's 100,000 gas at 2 Wei each. Now, while her code runs, that gas remaining counter is going to decline. Going to decline more for a big operation like writing to storage. And then here's the interesting part. Let's say that she zeroizes a word of storage. So remember, that's an opcode that actually has a negative cost. Her gas remaining never goes up, so your gas remaining can only go down. In fact, even writing a word to even zeroizing a word in storage actually has a gas cost of 5,000. But notice that there's this gas refund, which is now 15,000. So the net of that is like getting 10,000 back. But notice that you can, at a maximum, only use the initial start gas value worth of gas. That value can only go down to 0. It can never go up. If you execute an opcode with negative gas, what happens instead is that this gas refund goes up. And then at the end, if the transaction finishes successfully, you compute the refund that goes back to Alice's account by first giving her back all of the gas that's remaining, and then giving her back whatever gas refund accumulated from opcodes with a negative cost. And of course, those are going to be multiplied by the gas price she was willing to pay, which was 2, and her account balance will get the rest back. So notice that it's down from 1 million where it started, but she didn't have to actually pay for all of the gas that she didn't use. So it's important to recognize that running out of gas is a really bad thing in Ethereum. If you run out of gas, your transaction obviously halts. You can't execute any further. But also any changes that you've made are undone. So you basically go back to where the system goes back to where it was before the transaction started. The only change that's actually persisted is you don't get back any of the gas that you actually used up. So how can you avoid running out of gas if you're programming a contract? Well, fortunately, you can do introspection on the amount of gas that you have to work with, and you can maybe decide to do things 2 different ways depending on how much gas you have. So in Solidity, this gas left is a global function that you can call that tells you how much gas you have remaining. And in this example, you can see sort of a toy example, but this program decides based on how much gas is remaining either to create a new contract, which is pretty expensive, or if there's not that much gas left, to just reuse an existing contract that's being passed in. There's some other ways to interact with gas in your programs. So in Solidity, you can look at the price being paid for gas in this transaction. So maybe your program will do different things if gas is currently cheap or expensive. You can look at the gas limit for the entire block if you want to. And there is message.gas, which is just an older way of, it's equivalent to the gas left function. The other very important tool for programmers to manage gas is that you can limit the amount of gas that you pass on to another contract that you might call. So let's go through an example here. So contract A is called with 5,000 gas, but notice this .gas modifier, which is the Solidity syntax when you're calling another contract and you want to limit the amount of gas being passed on. Contract B is going to start executing with only 1,000 gas. And in this example, contract B is actually going to do the same thing, and it's going to pass only 500 gas onto contract C. Now notice that contract C has an infinite loop, so it's going to burn all of that gas. No matter how much gas was passed in, it would eventually burn it all up and have an out of gas exception. But notice that since B only passed 500 units of gas onto contract C, B still has some gas remaining so that it can continue execution, and it can actually return a result, and the entire transaction can still run successfully. So if you don't limit the amount of gas that you pass to another contract and it runs out of gas, then by necessity you'll also run out of gas, and you'll get sort of a propagating out of gas exception. So it can be smart when you're calling another contract to limit at least a little bit the amount of gas you're passing on, so if that contract happens to run out of gas, you can have a little bit left to clean up and finish executing successfully. When miners are looking at which transactions they want to include in their blocks, they can include whichever transactions are the most profitable to them. And usually that means they'll include whichever transactions are willing to pay the highest gas price. So there are a couple of websites that will show you statistics for this. Here are some that I just pulled from ethgasstation.info. But you can notice that the confirmation time is much higher if you're paying a lower gas price. So if you pay a higher gas price, your transaction is likely to get picked up and included in a block much more quickly. And they actually have recommended values, standard and safe low. These are kind of normal values, so this is a typical value today. But they have a value if you want your transaction to be confirmed very quickly. You can pay a higher gas price, and that's going to mean miners will prioritize your transaction over others. Miners are also limited by a global limit. So there's a gas per block, which controls the total amount of gas that all transactions within any one block can use. And this is something that can change slowly over time. So there's actually a mechanism for miners to vote on this to raise or lower the limit. But you can look at the chart. This is one provided by etherscan.io. And you can see that the amount of gas consumed per block, miners have voted to gradually raise that. So how much does gas actually cost in real terms? Well, it costs about 1.5 gigaway, which is actually about 1/1000th of an ether per unit of gas. And if you multiply that out at today's market prices for Ethereum, you can see that an individual 1 unit of gas is very, very small. It's like a millionth of a dollar. But for some of the more expensive operations, like creating a contract, it's already on the order of pennies. So not really expensive, but if you're doing a lot of work on the system, costs are going to add up quickly. And it's important to remember that Ethereum is not designed to be a distributed computing platform. So it's not designed to compete with Amazon Web Services or Microsoft Azure if you're doing really expensive matrix multiplications or something like that. It's really just sort of to control basic logic about where money goes. If you want to do expensive computation, you probably shouldn't be performing it directly on the Ethereum network. So one kind of interesting note, the fact that gas prices actually fluctuate and change means that arbitrage is possible. So what you can do, you can try and bank gas when prices are very low, and the way you bank it is actually by writing a bunch of words to storage or creating a bunch of contracts. And then when gas is more expensive later on, you can zeroize those words in storage or delete those contracts to get some gas back, and do an expensive computation using your freed up gas that you sort of banked when prices were lower. So gas token is a pretty clever smart contract that will sort of handle some of the plumbing of that for you. The caveat is that because you only get half your money back if you delete a contract or if you zeroize a word in memory, gas prices need to fluctuate by more than a factor of 2 for this to be worth your while. But it is something you can do that's quite clever. The simpler thing you can do, of course, is you can try and run your transaction. You can try and wait to run it till gas prices are lower, typically in the middle of the night. So if you have flexibility about when your transaction runs, of course you can wait and try and run it when gas prices are lower. So here's a look at how much gas prices cost today and how they've been fluctuating recently. And indeed, you can see there's some fluctuation, not too much in a 24-hour window. But if we zoom out, if we look at, say, the last 2 weeks or maybe the last 2 months, you can see that there's a fair amount of fluctuation. And if we take a very long-term view since the system was created, you can see, fortunately, that the general trend is that gas prices have been going down. You can also learn about gas by looking at a blockchain explorer that actually parses blocks in the network. So, for example, this is etherscan.io. And, well, first of all, within a specific block, we can look at what the gas limit was, 8 million gas, and how much was actually used. And look, you can see, almost that entire limit was used by this block. We can also look at a specific transaction and see how much gas it used. So this transaction used about 52,000 gas. And you'll notice that that was both the gas limit and the amount of gas that was used by this contract. And you might think, wow, that's kind of interesting. That programmer must have really gotten lucky and nailed it. They provided exactly the amount of gas that they needed. But if you think about it, you can simulate your transaction locally. Most of the time, at least, you can figure out exactly the amount of gas that you need. So it's not too uncommon to see people submit a transaction that has their gas limit is set to exactly the amount that the transaction is going to need to run. And again, there's no major cost in having a higher gas limit that you actually need because you get it back as a refund. But often people submit exactly the amount that they need. So to summarize, gas is a necessary evil for the network, and it's something that every programmer has to think about for 2 reasons, really. One is that, like I said, you don't want to get those out of gas errors. Those are really bad because then your program won't have any effects, and all you'll do is pay for burning up gas that had no point. But second of all, even though it's a necessary evil and we need it to pay miners and to limit resource consumption, if you're a programmer, you want to use as little of it as possible. And in particular, classic metrics like the running time of a program, how much memory it consumed, those don't really matter directly in Ethereum. They only matter because they cost gas, but gas is, for the most part, the single number that you're trying to optimize when you're developing an efficient program. So this is something that compilers can help with. If you're developing a compiler for a language like Solidity that compiles to EVM, you should try and have your compiler optimize for outputting EVM code that uses as little gas as possible to actually implement the program. And if you're a programmer, you should definitely be thinking about how to optimize the programs you're writing to use less gas. There's a lot of ways to do this. I'm not going to get in depth here, but at a high level, just as a simple example, you should avoid storage whenever possible. And when you have to use storage, you should try to use it efficiently. Remember, storage, one of the most expensive things you can do in Ethereum. So that's the story on gas. Like I said, it'd be great if computation were free, but it's not. So just a fact of life, whenever you're developing smart contracts, you're going to have to think about how much gas they're using.